Hey everybody, it's Mr. Francis, and this is my quick review for Chapter 10. As we saw, Chapter 9, Chapter 10, our focus is on compounds. It's on the arrangement of the atoms in a compound, the bonding of those atoms. Chapter 10 takes the bonding aspect a couple steps further. We are going to use things that we focused on in Chapter 9. We talked about drawing these Lewis structures. So we want to use those same rules for drawing Lewis structures as we go through it. But the important aspect in the first part of Chapter 10 is the fact that we are dealing with three-dimensional models. And in fact, in the next slide, you can see the arrangement and the structures for boron trifluoride and phosphorus trifluoride. Both have the same general formula, but note the arrangement of the atoms in each one. In the boron trifluoride, it's arranged much like a triangle. Phosphorus trifluoride, now it's arranged much like a pyramid. So we're going to talk about why we see the difference in each of these. We focus on, like I said, the three-dimensionality of it. And the three-dimensionality of it comes from this idea known as VSEPR, valence shell electron pair repulsion theory. And that's where we're going to start off. We'll get into valence bond theory here in a little bit. The definition for valence bond theory, as you can see, I want you to point out two factors. We're going to talk about arrangement and geometry. So you're going to hear me use those two terms quite a bit. Sometimes with geometry, you will hear me use the word shape also. But here's the key. We drew our Lewis structures. We want to focus just on the central atom. Just the central atom, not the outer ones. The central atom, and we want to see, as it says, the electron around the central atom, the electron pairs are kept as far away from one another as possible. That's where we're going to get our three-dimensionality. Like I said, arrangement and geometry are two very distinct terms. Arrangement, as it says here, the total number of electron pairs on the central atom. That's going to be key. And we're going to talk about what we mean by total pairs. Geometry is going to be based on what the arrangement is, and then of those pairs, how many of them are lone pairs on the central atom. Okay, figures 10.2, 10.4, and 10.8 are going to be figures that I want you to go back to quite often in this chapter, because again, it's tables that we want to reference. We don't want to memorize. The whole idea is we want to keep electron pairs as far apart from each other as possible. So as you can see here for 2, 3, and 4, hey, if I want to keep two things as far apart from one another as possible, one over here, hey, you've got that linear arrangement. But look at 4 here. We got 4 pairs of electrons on the central atom. They're not arranged like a square. It's a tetrahedral. Because again, look at this angle, 109.5 degrees. When we're dealing with 5 and 6, because again, we talked about the expanded octet in Chapter 9. Again, we get the different arrangements. When you have 5, of those 5 pairs, 2 of them are arranged above and below the central atom. The other 3 are arranged around the central atom. That's where you get the name trigonal bipyramidal or bipyramidal. And an octahedral, hey, now you've got 4 pairs arranged around the center, one above and one below. And this is kind of give you a model picture of each of these arrangements that we're focusing on. Now, I mentioned electron pairs and the number of electron pairs, but when we get into, actual determinations, we are looking at the positions of the atoms. So that's where you get the terminology linear, trigonal, planar. Those are all locations for the atoms, but they are based in part on the electron pairs that we see. This is the first part of Table 10.4. And what I want you to pay attention for in this table are these 3 columns. The total ties in with arrangement. The bonding and lone pair, these 2 columns tie into geometry. And that's how I want you to read the columns with this. So as you can see, the 4 total electrons, hey, that's a tetrahedral arrangement. But 4 and 0, 3 and 1, 2 and 2. So how we break down those 4 electron pairs can dictate the different geometries that we see for the central atom. And again, the same thing with when we have the trigonal bipyramidal and the octahedral. Again, your total column here ties in with arrangement. The bonding and lone pair columns tie in with geometries. So go back and use table 10.4 and 10.8 as you're going through the homework and as you're going through the quizzes and such. Have these available to you. Okay. Now, VSEPR does take into account resonance structures, does take into account multiple bonds. And here's the key. VSEPR, if it's a multiple bond, it's just one pair. That's all we're going to look at it as. If it's a resonance structure, and remember resonance structures, you can have multiple arrangements. We're only going to choose one of them to make our statements. Okay, so you're going to be given examples where you're given a formula and you're asked to identify ultimately the geometry. You're going to get the arrangement and geometry. Everything starts with the electron dot formula. Everything starts with the Lewis formula. And then from there, you can follow the steps. So the same thing here. Here's the beryllium dichloride and the nitride ion. They drew the Lewis structures for each one without the Lewis structures. And then you can identify your arrangement and geometries for each one. But again, everything starts with the Lewis structure. Okay, you can't look at a molecule and say what its arrangement and geometry is just by what the formula of the compound is. It doesn't work that way. Bond angles are key because again, we want to keep the atoms as far apart from each other as possible. Lone pairs, and again, remember a lone pair is just on the central atom, not bonded to any other atom. It needs more space. And what happens when it needs more space? It affects the angle that you see for the molecule. And that's what you see in the example here. And the same thing with the multiple bonds. They require more space. And that's why we're going to consider these just as one pair or one set of electrons in the structure itself. Again, when we have the expanded octet, you can see the different structures and the arrangements. Note where the lone pairs sit in these structures, okay? You can distinguish where you find them in the structure itself. And the same thing with each of these. So if we have this question, you want to find the geometry of the molecule. Again, we've got the Lewis structure, so that's where we start with. We count up the total pairs. That's going to give us our arrangement. And then, hey, we've got 4 and 1. That's going to be and again, this seesaw geometry for the molecule. Switch gears a little bit. We talked, if you remember in chapter 9, we talked about polarity and the attraction of the electron pairs to the atoms. There is a measure for that. It's what we call a dipole moment. So if we've got a bond that has that unequal sharing, it forms this dipole. And that dipole allows it to align to charged plates. It also allows it to be attracted to water. We use these signs as delta plus, delta negative to dictate which is the more electronegative atom, which is the more electropositive atom. We use an arrow to dictate the movement. So at the direction that the arrow is pointing, it always points to the more electronegative atom. Dipole moment and molecular geometry are related. They are tied in together. And you see that in table 10.1. But I like this statement here. The geometries that have dipole moments of 0, they all have 0 lone pairs. Go back to table 10.4 or figures 10.4 and 10.8. Look in those columns for the ones that had the 0 lone pairs. And if you look at this table, each one of these that have the 0 dipole moment, each one of these geometries, 0 lone pairs in the geometry. And it can affect properties because the dipole moments can converge upon each other or they can cancel each other out. And you can see the difference in some physical properties for this. VSEPR gives us the three-dimensionality. Valence bond theory gives us in an orbital diagram how the electrons are are combining together and how those valence electrons of the central atom and the outer atom are combining together. And it talks about how we're going to form a bond. And the key with the bond is this overlap. We're overlapping orbitals. And the most that we can put in those overlapped orbitals are 2. And here's a great example. You've got the 1s orbitals for hydrogen. They overlap together. There's our bond, that overlap bond that gets formed. And the orbitals don't have to be the same. They can be different orbitals. It can be the 1s of hydrogen, the 3p of chlorine. They can overlap together, and you've got your bond. The greater the overlap, the stronger the bond. We talked about bond strength in the last chapter, so we see that. There's an interesting aspect with valence bond theory. It comes up with what we call hybrid orbitals. You know the term hybrid means combination. So what we're seeing with these hybrid orbitals is a combination of the s, the p, the d orbitals. They combine together to actually form a new orbital that is used for the bonding. There are 5 types, and as you look at this table, the 5 types, sp, sp2, sp3, you look at the combinations lead to the type of hybrid orbital that gets formed. But what's great about this is that the hybrid orbital and the arrangement are tied together. You will never see a central atom that has an sp that's using the sp3 hybrid and not tetrahedral arrangement. Okay, they're always tied in together. And again, you're going to see questions that are asking you to identify not only the geometry, but also the type of hybrid orbital. Everything starts with the electron dot formula. So you want to keep that in mind. Here's boron and the bonding that you see in boron. And they tell us, hey, we're going to use this sp2. So we're going to take this valence s, we're going to take 2 of these valence p orbitals, and we're going to combine them together to form this new hybrid. And then it's this hybrid that forms our bonds. We see the same thing with oxygen. Again, from the structure, we've got tetrahedral. We go back to table 10.2, tetrahedral arrangement, sp3 orbital. Look at the combination. So we're going to take the s, we're going to take all 3 of the valence p orbitals, and we're going to combine them together. That gives us this new orbital. And note how the electrons, those 6 electrons right here, are filling up. They fill up according to Hund's rule. So an electron into each orbital, and then it starts pairing up. And you can do the same thing. Here's xenon tetrafluoride. Xenon's going to have, count it up, we got 1, 2, 3, 4, 5, 6. So we got 6 total pairs. 6 pairs. Hey, that's a octahedral arrangement. Octahedral, sp3d2. So the s, all 3 of the p, and then 2 of the d orbitals. There's our new hybrid that gets formed. Valence bond theory also takes into account multiple bonds. And with multiple bonds, you actually get 2 types of overlap, what we call a sigma bond and a pi bond. And it's important to note the types of overlap they involve. The pi bond's key because it's an overlap that's above and below the central atom. And that's what you see here in this example. Here's the pi bond above and below the carbons with that. And you can see that here in the examples with ethylene, the C2H4, and then also the ethene, the acetylene, the C2H2. And then the hybrids being formed with it. And I'll let you go through the rest of this for the rest of these problems. So if you have any questions, please get a hold of me. Keep working, keep up the good work, and I'll talk to you soon. Bye.